Hello everyone. In this video, we will introduce our work, Confidence-Driven Multi-Scale Model Selection for Cost-Efficient Inference. First, let's start with a simple question. Do we really need to use the largest model for every query? Different queries vary significantly in difficulty. Running a large-scale model for every query is impractical, particularly for resource-constrained settings. For easy queries, even a smaller model can answer correctly. If we know what kind of queries are easy for models, we can potentially save computational cost through model cascading. When people solve problems, they assess their own confidence. Can LLMs do the same? Yes, this falls under uncertainty quantification. Previous work shows that LLMs produce well-calibrated probabilities when selecting among multiple explicit choices. They refer to this as PT, the probability of truth. They also proposed PIK, the probability of I know, which measures the likelihood that a model can correctly answer a given query. It requires training an additional classifier. Some researchers have attempted to extend confidence estimation to generative tasks, such as sampling multiple responses or using average token probabilities, but the performance is modest. So we propose first token confidence. We prompt the model to respond in a specific format and measure the probability of the first token being answer. For the work of LLM routing, recent efforts like Route LLM learn to route queries from preference data. RouterBench provides a comprehensive comparison of different routing methods. Most of these rely on offline training or task-specific heuristics. Our work differs by using the model's own confidence signals for dynamic instance-level decision-making. Now, let's introduce our proposed method. For multiple-choice questions, PT is obtained from the model's probability distribution over answer choices after prompting answer. For generation tasks, we use a different prompt and measure the probability of the first token being answer. We trained a multi-layer perceptron using hidden states from the 24th transformer layer as input, with supervision indicating whether the model correctly answered each query. Our method first assesses PIK for smaller models. If PIK or PT fall below a predefined threshold, the query is escalated to the next larger model. In our experiment, we evaluate on MMLU, a multiple-choice benchmark assessing general knowledge across 57 subjects. We use Elame instruction-tuned models 3B8B, 70B, and Quen 3 series 4B, 8B, 32B. We adopt Kaplan's approach. The computational cost is defined as CC equal 2 Here's a concrete example showing how we calculate gigaflops for the 3B to 8B to 70B configuration. The key finding is that 8B to 70B achieves 22% accuracy, comparable to the 70B model's 83.57%, with a 36% reduction in computational cost. McNemar's test shows no significant difference. On Quen 3, the 8B to 32B cascade achieves slightly higher accuracy than the full 32B model, while saving approximately 33% of compute, confirming generalizability across model families. We also tested with GPT-4o. Since OpenAI does not disclose parameter counts, we use output tokens as a proxy for compute cost. The 70B to GPT-4o approach slightly improves performance while achieving approximately 60% cost savings in token usage. We conducted a systematic cost evaluation using publicly available token pricing from Sambanova and OpenAI. Direct GPT-4o usage costs 0.928, while the 70B to GPT-4o cascade costs only $357, achieving over 61% cost reduction. We also evaluated on PopQA, a large-scale open-domain QA dataset, to test generalization to generative tasks. The 8B to 70B strategy achieves the best accuracy and lowest hallucination rate among cascade settings, saving over 7% in cost with only 1.91% performance drop. The ablation shows PIK is useful. Performance drop is significantly greater without it. However, even relying solely on PT still achieves competitive performance, which is practical for API-based settings where hidden states are not accessible. You might wonder, what is the best threshold for PV-T? We conducted a sensitivity analysis to find out. The sensitivity analysis shows that thresholds around 90% strike a good balance. With PIK, accuracy remains relatively stable even when the threshold is lowered to 50%. We further tested OOD generalization using GPQA, a graduate-level benchmark that represents an out-of-distribution setting relative to MMLU. Here is the experimental result. The substantial difference in computational cost savings between MMLU and GPQA highlights the difficulty of extending the method to OOD applications. However, the PIK classifier is conservative with OOD queries. Among 67% were answered correctly, showing the classifier remains useful. We propose a confidence-driven strategy leveraging both PT and PIK. It matches the largest model's performance while reducing compute cost and cuts token usage by 60% when applied to GPT-4o. We demonstrate effectiveness in both in-distribution and OOD settings and show promising results on generative tasks. Future work should focus on refining confidence estimation for better generalization. That's the end of our presentation. Thank you for your attention.